Okay, this is the latest project. This is a Nixie tube clock where all of the driving circuitry and counting circuitry is not done with any transistors or chips. It's done with about 100 trigger tubes. So what these things are they're basically like cold cathode fibertrons, and they're filled with neon gas, and they have a cathode, an anode, and a trigger electrode. And what happens is that you can apply a little pulse to the trigger electrode, and it will cause ionization between the anode and the cathode, and it will cause the tube to strike, and it will remain struck at a lower voltage than the initial voltage it was operating at. So you can use these in counting circuits. If you look here, this is the beginning of the clock. Here's a row of 10 tubes. They're in a ring counter configuration. And what they do is that when one tube is struck, it applies a little bias to the next tube. And so when the next pulse comes in, it causes the discharge to move from one tube to another. So in this counter right here, there's 60 hertz coming in, and there's 10 tubes. So at the output, we'll have 6 hertz. And then that goes into another array of 6 tubes, and that divides it down to get 1 hertz. And then we have another row of 10 to give us 1 over 10 hertz. And then a row of 6 to give 1 minute pulses, 1 over 60 hertz. And then from there, we have an array of 10 tubes that gives us the minutes. A row of 6 that gives us tens of minutes. A row of 10, and they're driving tubes as well, that give us the hours. And then this special one right here, this row of 3, that gives us the tens of hours. So right now it's basically in its prototype state here. And I just want to make this video because I'm going to be taking this all apart and reassembling it on a piece of wood or something. And I just wanted to get this video because I could take it apart and break it. So just to show you, give you some more insight on the operation of these, I have this ring counter right here hooked up to the oscilloscope. And if we look here, we can see the 60 hertz going in, and then here are the output pulses. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we get another pulse. So that's just a brief overview, and I think now I'm going to go into more detail of the schematic and how it does all its logic. Okay, so this is a block diagram of the clock. See, it starts with 60 hertz, gets divided down to 6, divided down to 1, 1 over 10, and then 1 over 60, and that's 1 minute. Then we go over to the display side. We have a 10-stage counter. That gives us our minutes. We have a 6-stage, which gives us our tens of minutes. Then we have another 10-stage, which gives us our hours. And then a 3-stage, which gives us our tens of hours. Just ignore this little bit of muxing going on right here. I'll get into that later, but that has to do with resetting this stage back to 1 after it reaches 12 o'clock. So to really explain how this clock works, I have to go into some of the fundamentals of how trigger tube circuits work. So this is a fundamental, like, textbook example of a trigger tube ring counter. The special thing about these tubes is, as I've said before, is that their maintaining voltage is less than their striking voltage. So there can be a high voltage applied to this tube, say 100 volts, but it won't cause it to strike. But if you give it a little impulse of energy to the trigger, it will strike and maintain to say about 50 volts. That's like a negative resistance type thing, and it allows these to be used in counting circuits. So here we can see the circuit. All of the anodes of the tubes are connected together and go to a common anode resistor. And all of the trigger electrodes are connected with a capacitor to a common trigger line. And the important thing about this right here is that the amplitude of these trigger pulses must not be higher than the actual trigger voltage needed to turn these tubes on right here. That's important. So let's just assume that this tube is on right here. That means that there's a current flowing through it, and there's a resistor right here, so that means there will be a voltage dropped across this tube right here. And that voltage, what it will do is goes through another resistor, and it will bias this tube very slightly. Again, not enough to make it turn on, but just very close to that. And then what happens when a pulse comes through here, it's capacitively coupled, and this pulse will combine with the bias of this tube coming into there, and it will cause this tube to strike. But then we have the problem of how do we turn this tube off? Because if just one caused the next to strike, the whole row of them, it just start with one, and then say all 10 would be on. So how do you get the previous one to turn off? How do you get it to commutate? That's where these capacitors come in. When this tube is on, this capacitor gets charged, and since there's a voltage drop across here, the seen voltage across this tube is slightly less than the actual anode to ground supply. But this tube right here is off, so the capacitor right here is discharged. So what happens when this tube first strikes is that this capacitor will act like a short for a very short period of time and cause full anode voltage to go across the tube. So a whole bunch of current will flow through it, and that will cause this voltage right here to drop below the holding threshold of this tube, which will cause it to go out. So then we've transitioned the glow from this tube to the next tube. And then the cycle just repeats to the next tube and then back to the first. So what we can do is we can take a trigger pulse off of the cathode of any of these tubes, and that will be divided by 3 of the input pulses. So again, that's the theoretical circuit, but in reality, and with these crummy Russian tubes, you have complications. So the complications arise from the fact that none of these tubes are matched, none of them to each other. Like initially when I tried to make this, I spent like hours measuring the threshold and the holding potential of each tube and then trying to calculate resistor values to use for it, but they just don't work. These are not consistent enough of a device to be able to do that. But you can get around that by just adding adjustments. So if you see here, we originally had just one resistor here, but now we have 2. We have a 100K potentiometer right here, and that sets the bias for the next stage. And we have a 1 meg potentiometer right here, and that sets the total current flowing through this tube. These vary widely in the current they want and in the voltages they have, and you can't get away from having this adjustability if you use these tubes. There are a lot better trigger tubes out there, but these ones are only about 50 cents each, and the other ones, the good ones, they're like Z700s or something. They're like I think $2 or $3 each. So it's worth to have these extra. It's worth to put up with these crummy tubes because they're like a whole bunch cheaper. So this is the actual circuit for one of the divide by 6s. So you can see the adjustments here, the capacitors and the lines. I should go into the power supply as well. uses the voltage doubler. These are voltage regulator tubes. I think they're OA2s, and they have about 180 volts regulation voltage or something like that. And then the way that the Nixie tubes are driven, they're driven on half-wave rectified voltage so that the driving tubes can commutate themselves, and then 27K is going to the anodes. Here is the supply for the 60 hertz to the first stage, just a 500K potentiometer going to the negative 180 volt source, just with some 10K limiting resistors. Okay, so I think it's now time to go back to sort of some of the logic that has to be done in this clock, because you can't make it work with just counters. Well, actually, I think you can, but you need a whole bunch more tubes. So it's worth it to go through this extra logic right here. So if you look at a clock display, a 12-hour clock display, the hours indicator doesn't just reset. Well, it can reset if you just have 12 stages, but I just wanted to use 10 instead. So if you go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0, okay, well that's fine. And then 1, 2, but then it goes back to 1. So you have to have some logic in here to transition it back to 1, because otherwise this would just go like 1, 2, 3, 4, 5, 6. So I had to implement some logic for that. And the way that I did it, I just thought of it as different states. So in state 1, I just display 0 right here. And then once I get a pulse that says that the hours indicator has transitioned back from 9 to 0, okay, I transition to state 2, and that displays a 1 right here. And then what will happen is that this will keep counting. So this will keep counting 1, 2, 3. And when it reaches 3 again, I take a pulse off from there to transition me to another state, state 3. And what this does is it changes the clock source for the hours. So you see normally right here, this gets 1 hour pulses. It increments the hours every hour. That, of course, that makes sense. But what this does is it changes that from 1 hour pulses to 6 hertz pulses. So what that will do is this will quickly go through the stages 1, 2, 3, 4, 5, 6, 7, 8, 9, and then go back to 1. And once it cycles through all those and goes back to 1, I take a pulse off from here, and that transitions back to the 0 right here. Now for the actual schematic of that. Here's the hours counter. You can see it's just a 10-stage ring counter, and then here are the driving tubes right here. So these are the things that actually drive the Nixie tubes. And the way that these work, these just take some bias off of right here, the cathodes, and that just gives them enough voltage so that they always turn on. And there's AC, well there's half-wave rectified DC, so it commutates through 0, so that these tubes will be self-commutating and turn off when the bias is removed. And here's the logic circuit right here. So here are the 3 states. Here's state 1, and this is triggered when the 1 hour pulse is received. So that means it's gone through its cycle, and then 1 is displayed to the screen, so this is 1, so cathode 1. And then this is state 2 right here. That gets triggered when the tens of hours gets pulsed right here. So this is 0, cathode 0. So this will display a 0 to the hours, and then now that this is triggered, this will display a 1 on the tens of hours spot. And then here's the special one right here. This is does the switch over. When 3 gets turned on, so it will be displaying 13 right now. This tube will get turned on, And then what that will do is it will trigger this very sensitive relay, and it will change the clock source for this module from 1 hour to 6 hertz. So it will quickly cycle through, all while staying into the state until it's reached the end, gone back around, and reached 1. And when it reaches 1, the next tube triggers and it displays a 0. So, sorry, that's quite confusing, the way I explained it, but it's actually relatively simple once you get your mind around it. So, about this relay. This is actually a pretty old relay. I'm not quite sure when it's from, but it's about 2,000 ohms, and it takes 1 milliamp to make it trip. So what I'll do is I will change the clock to set mode, and it will quickly cycle through, and we'll be able to see that relay trigger and for it to do its little reset routine. Okay, so the nice thing about these ring counters is that in order to make them oscillate, all you have to do is just decrease the anode resistor, and it will self-oscillate and allows you to fast set the clock. Okay, did you see what it did there? Once it reached 12, it quickly went to 13, and then this changed the clock source back to 6 hertz. Let's see again. Oh, it missed that time. Let's see if it will work this time. Okay, worked that time. So let's try to maybe slow it down a little bit so you can see it work better. So instead of going there, put it right here. Okay, I'll pause this for a little bit. Okay, so that's how it works. That's how it does its little reset routine. I'll just go through a one-over of the whole thing again. Here are the voltage regulator tubes. I didn't show that earlier. Power transformer. Not much going on there right now. Yeah, there's still some work to do on it. It sometimes misses that reset, so I might have to adjust the trigger point of one of the tubes. As you can expect, setting this thing up is a nightmare. Each tube has 2 settings on it, and of course each setting affects the next tube, so it's quite a pain to adjust if it isn't quite working. But the nice thing is that it sort of tells you what's not working, because, for instance, one of the tubes will get stuck, and it won't transfer to the next because I don't have the bias voltage adjusted right. So that sort of tells you how to fix it. You know, because they light up, they're sort of like a self-diagnostic tool. In case you're interested in any of the construction, it's just constructed on little pieces of copper-clad board with slots cut out. And I used strips of, I think, 12 gauge copper wire for the two supports. And then, geez, I'm not quite sure what that other one is, 16 gauge for the trigger supports. And the tubes are just sort of floating in midair right now. They're not really secure. Something I forgot to talk about was aging of these tubes. When I first got these and tried to build something out of them, I couldn't get anything to work at all. The tubes were just too different from each other. Even with the extra potentiometers in there, it just didn't work. So what I did was I just lined these all up on a row and ran them for about 2 days on about 4 milliamps per tube. And usually these are rated about, I think, 1 or 2, so that's kind of pushing them hard. But after I did that, I was able to make successful ring counter circuits with them. That's quite important if someone else wants to attempt with these types of tubes.